Hi everybody. Thanks for sticking around for the last talk of the day. So today I'm going to tell you about UniRec, a Unimodular-Like framework for nested recursions and loops. This is a paper that I did along with my students, Krishan Sundararaja and Sharada Sonia. Before I get started, I do want to mention that Krish, who is the first author on this paper, is on the job market this year. He wasn't able to be here for visa reasons, but if you're looking for somebody who really knows the ins and outs of compilation, stuff like that, please give him a look. There's a lot of words in this title. Not all of them might make sense to everybody. There's also a lot of background in this talk to help fill in those gaps. So even if you decide you don't like the UniRec, hopefully at the end of this talk, you'll know a little bit more about how compilers reason about things like loops and recursion already. So let's just dive right in. What I have here on the left side of the screen is a really simple doubly nested loop that just computes the vector outer product of two arrays, x and y. So classic doubly nested loop, classic linear algebra kind of operation. And this kind of linear algebra operation, even if not necessarily vector outer product, shows up in stencil codes, it shows up in partial differential equation simulations, it shows up in machine learning all over the place. And because these sorts of loop programs are so important in all of these kinds of domains, compiler writers have spent decades coming up with different kinds of transformations that we can do to these loops in order to improve their parallelism, in order to improve their locality, to vectorize, and to map them to GPUs, things like that. And so when you give a compiler, a polyhedral compiler, for example, a nested loop program, they can do things like loop interchange and loop tiling and loop skewing to improve parallelism and locality in these programs. But we don't just care about loop programs, and I don't just care about loop programs. I care about programs that combine loop and recursion. So here is a simple little program that essentially also does vector outer product, except now one of those vectors is threaded through the leaves of a tree. So I have an outer loop that just walks over an array, and for every element of the array, it multiplies it by a value that's stored in a tree, and that tree is traversed recursively in this tree function here. And this is, even though this particular example is contrived, these kinds of combinations of loops and recursion do show up in programs like Barnes hut simulation and things like that. It shows up in data mining programs like nearest neighbor or clustering algorithms. It shows up in graphics algorithms like ray tracing. And a question that we and a lot of other people have been trying to answer over the last few decades is, what can we do here? When we have these kinds of programs that don't deal with loops, but also deal with recursion over complex data structures, how can we optimize it? And it turns out there's actually a lot of interesting answers here. There's a lot of things that we can do, a lot of analogs to these kinds of transformations that work for recursive programs. So to explain those, let me start by turning this combination of loops and recursion into something slightly simpler, which is I'm just going to turn that loop into a tail recursive program. So that way we can just think about recursion, but fundamentally any loop can be thought of as a tail recursive function, and so still the same program, right? Now, when a compiler sees a doubly nested loop like this, for example, a polyhedral compiler, the most important thing to do is to understand that each one of those loop bodies executes n squared times. And so I need to think about each individual instance of that loop body that's executed, each value I and j, and I do that using, I can get there, this little thing that we call an iteration space. It's basically just a representation of each individual instance of aij is equal to x I times yj. And I've just drawn some arrows here that shows the order in which those instances executed just corresponds to the execution order of these loops. And I can do exactly the same thing for the tree code, where I can just think about every instance of the array function on the A dimension there and every instance of the tree function on the T dimension there. It's the same thing, just a dynamic instance of that particular computation. And once I start thinking about these dynamic instances, now I can think about the different kinds of transformations that I do to programs as basically changing the order of these instances, changing when these things happen, rescheduling these computations. For example, loop interchange, one of the simplest transformations, just takes this I and j loop and swaps it. J goes on the outside, I goes on the inside, and that has the effect of just changing the order that those instances happen. It just changes the schedule. And similarly, and interestingly enough, there is an equivalent when we're talking about recursion. So in this original code, the array function calls the tree function that goes in and does the work. But if instead I go in and make the tree function call the array function, so now I walk over the tree, and for each node of the tree, I walk over the array, I've changed what this code does and fundamentally done exactly the same transformation on the recursive program. It's tilted, it's switched the schedule around in exactly the same way. It's an analogous transformation. Loop reversal, another classic optimization, or another classic transformation, for example, might take this I loop and just run it backwards, counting down instead of counting up. Has the effect of changing the order of the loop of the instances again. And interestingly enough, there is yet another analogous transformation in the recursive world, even though I don't have access to those same induction variables in the same way that I do in the loop. What I can do is take those two statements, the actual computation and the recursive function, and just switch them from preorder to postorder. And if I do that, that has the effect of running the array loop in the opposite order, the array code in the opposite order, right? And so over many years, we've come up with lots of analogs between loop transformations and recursive transformations. Loop interchange corresponds to recursion interchange, like I just showed you. Loop reversal corresponds to changing from preorder to postorder. Strip mining, another classic transformation, corresponds to basically doing some inlining and outlining of a recursive function. And then loop tiling, which is sort of the big transformation that people like to do for locality, corresponds to, well, combining recursion interchange and inlining. So you can do the equivalent of tiling except for recursion. Now, what's nice about these kinds of transformations is that when you start to compose them together, they give you lots of different effects, and sometimes, in fact, you need to compose them. Transformations by themselves that change these schedules aren't necessarily going to give you the correct code. You can get situations where if I do loop reversal on a loop, I get broken code, the code does the wrong thing. If I do just loop interchange on a loop, I get broken code, the code does the wrong thing. But if I do them both together, if I compose them together, I get a new schedule that gives me a different different order of operations, but the same result. And my code now works. So doing these kind of compositional reasoning about transformations is one of the fundamental things that these frameworks do. And so, in particular, these operations here, these transformations here, were put together back in the 80s by Paul Banerjee into something called the Unimodular framework. And back in 2019, we talked about how to take those same kinds of transformations in the recursive world and put them together into a compositional framework called polyrect. Right, so that's kind of where things stand. There's a lot of analogs of these transformations. We can reason about them in the loop world. We can reason about them in the recursive world. Those of you that might have seen the polyhedral framework or the unimodular framework before know that there's actually a transformation that's missing here. The transformation that people will use to, for example, deal with wavefront codes or stencil codes is called loop skewing, which I'll talk to you about later if you're not familiar with it. And up until now, it's actually not been clear that there is even an analog to that kind of transformation in the recursive world. So the unimodular framework can deal with loops and can do all of these things, but it can't handle recursion. Polyrect, the existing recursive framework, can handle those first four transformations, but doesn't have an analog for loop skewing. And so what I'm going to tell you about today is something that does both. So it can basically do everything the unimodular framework can do, as well as everything the polyrect can do. And so UniRec is a general framework for handling loops and recursions. And in order to do this, we create a new representation of iteration spaces, those little bubbles with arrows between them, a new generalized approach for handling transformations, in particular for handling unimodular transformations, the full set of unimodular transformations. And then we show how we can create a compositional framework by modifying dependence tests and making sure that all of our transformations are actually safe. So here's the game plan. Like I said, lots of background. We get to learn a lot today. First, I'm going to tell you a little bit about polyrect and about how these transformations work in the first place. Then I'll tell you what loop skewing is and why that's hard to deal with. Then I'll tell you how we fix it, how we extend polyrect to make loop skewing work, make it all put, and then how we can put it all together to create a nice compositional framework. So the fundamental challenge when thinking about scheduling transformations is you need to actually represent those dynamic instances of a particular computation. It's a single line of code, but there's n squared instances of it, and the schedule of those n squared instances is what matters. So every dynamic instance needs some unique name that the compiler can reason about, and it needs to be able to place those unique names into a total order to represent the schedule. When we're talking about doubly nested loops like this, our names are just I, j tuples. I can literally just keep track of the value of I and the value of j to figure out the names of all the instances, and if I just put those in lexicographic order, that corresponds to the schedule of computation. When I'm dealing with recursive programs, it's not quite that simple because I don't have an I and a j. And recursion is not nice and linear in the same way that loops are. Here, I've changed my program from walking over a tree to just walking over a linked list instead because it makes the presentation a little bit easier. But it's basically the same thing. It's just an array function that calls on this function, or actually in this case, a list that does the computation. So what polyrect does to represent iteration spaces is it names everything using what we call a control word tuple. So here's what that is. Here's the iteration space that we're trying to generate. We're somehow trying to give unique names to each one of those bubbles. Okay? And we're trying to order it. What we're going to do is we're going to label each of the sort of core statements of these functions, both the recursive functions that are being called, as well as the actual computational statement n.x of y, blah, blah, blah. Okay? And for each one of these instances, I can think about a snapshot of what the stack frame looks like when that statement executes. Okay, so to execute S1 the very first time, I call the array function, immediately call the list function, and then the list function executes the statement. So the stack frame looks like T1 followed by S1, sitting on the stack. If I execute a different iteration, for example, this pink guy here, that looks like calling the array function once, recursively calling it, so I call R1. Then I go in and call the list function, which calls S1. And so the stack frame looks like R1, T1, S1. It's just a unique name for each one of these instances. I can name this guy, this purple guy, R1, T1, R2, S1. So that basically calls the array function once, then the array function calls list, which calls itself once, and then I call S1, or execute S1. And if I place an ordering on these labels, that it actually exactly corresponds to the ordering in the program itself, the lexicographic ordering of those control words exactly corresponds to the order they're supposed to execute. Very clean. This is the way that polyrec represents the iteration spaces and schedules. We didn't actually invent this. This we borrowed from some work that Albert Cohen did back in 2006. But what polyrec did come up with, and what the sort of key thing here is to represent all of these spaces, to represent this information about how we name instances and how we order them, we use what's called a multitape automaton. A multitape finite automata is a finite automata just like you're used to seeing, except instead of one tape with symbols on it, there's two or more tapes with symbols on them. In this case, a red tape and a blue tape. And every one of those control words you can think about as being generated by some accepting path through this automaton, where we take the red tape and concatenate it with the blue tape. Okay? So that's basically our iteration space representation. It's a finite representation of this recursive space. It works for lists, it works for trees, anything recursive. So how do we do transformations? Once we have these iteration spaces, that's not good enough. We actually need to know what happens when we do things like move interchange on. And so the way that we represent it, the way to think about transformations is you're mapping one iteration space to another iteration space. Every bubble in one iteration space maps to a bubble in a different iteration space. For example, if I do loop interchange to transform the purple space into the blue space, then the iteration 0, 1 in the purple space transforms into the iteration 1, 0 in the blue space, 2, 1 transforms to 1, 2, and so on. That's in the loop world. And the way that the unimodular framework, or the polyhedral framework, represents these kinds of transformations is you can think of it as a change of basis. I take my ij values in the purple space and multiply them by this little permutation matrix. It gives me u I prime j prime values in the blue space, corresponds exactly to the transformation. It's a renaming transformation. Rename I j I prime j prime. So here's what's cool. The unimodular framework uses linear transformations of linear spaces. That's essentially what it's doing here. It's taking these linear iteration spaces, doing linear transformations on them to represent all of their transformations, and because they're linear transformations, they compose very nicely. And so now I can compose together all of my transformations to think about a combination of transformations and what it does to my system. And I can do the same thing for recursion, because if I have my purple space here, this is my array and list code, has these particular labels, I want to transform it into the interchange version, this blue version of the code, which has slightly different labels. The exact labels don't matter so much, but what matters is it's just got a different set of labels. Same kind of renaming that's going on. This pink thing turns from T1 R2 S1 to R1 T1 S1. Don't worry about the details, that's the transformation that needs to happen. Similarly, I can think about the new name that I need for the other pink iteration. I should use better colors. But fundamentally, what we're doing here is we're rewriting one word into another word as part of this transformation. We're taking one sequence of symbols and turning it into another sequence of symbols. If you think about the way that automata work, how do we rewrite one word into another word? Well, we can use transducers. And polyrec uses multi-tape transformation transducers in order to do this rewrite. So for example, every time it sees a red R1 on the red tape, it turns it into a pink R2. Every time it sees a blue R2, it turns it into a light blue R1. And that produces exactly this rewrite. And so now I have a finite representation of my transformation using a multi-tape transducer. Multi-tape transducers are incredibly complicated. They do really crazy things. Okay, but they are still compositional. I can compose multi-tape transducers together. I can stick them to each other and create a new transducer. And in particular, I can compose an iteration space automaton with a transformation transducer to produce a new iteration space automaton that exactly corresponds to the transformed iteration space. Okay, so now I can do all of my compositional reasoning. Why can't I do skewing? Why doesn't loop skewing work? So what loop skewing does is it tilts an iteration space so that you can parallelize it, depending on how your dependencies are structured. So what it's going to do is it's going to take something like this purple iteration space here and tilt the iterations to create the blue iteration space. That's what a loop skewing transformation tries to do. And so, for example, iteration 1, 2 turns into iteration 3, 2. And the way that this works is that I use a transformation matrix that does a linear combination of dimensions. My I prime, the value in I prime is I plus j. And so that's exactly the transformation that I see. I can also skew in the other direction. I can tilt the matrices in the other direction. This we call negative skewing, and the reason we call it negative skewing is if you're subtracting one dimension from the other. Right, so in this case, I'm doing I minus j with my transformation, but this is still a single linear transformation. And here's what's really nice. Once you add skewing to your list of linear transformations, you actually have a complete transformation framework. The unimodular framework is about unimodular transformation matrices. These are matrices whose determinants are +1 or -1. And in fact, that represents every possible combination you can do of interchange, reversal, and skew on loops. Okay? And it goes in both directions. Any unimodular transformation is that. Any combination is a unimodular transformation matrix. So can we do this in polyrec? Can we do this kind of tilting in polyrec? Well, sometimes yes, we can. If I think about the renaming that happens when I do this tilting using polyrec control words, I do something like this. For every, in the pink dimension basically gets 1 plus 2 is what I'm trying to do. So I'm trying to add 1 from red and 2 from blue. And a transducer that works like this says every time I see a blue R2, I want to put symbols on both the blue tape and the light blue tape. Generates that transformation. And so I can actually tilt this. I can represent this transformation in polyrec already. And essentially I'm consuming a symbol off dimension 2, and I'm just adding an output symbol to each dimension. It does exactly this transformation. But what if I want to go the other way? If I want to tilt backwards. So I don't even know what that pink symbol should be, because I've got to somehow represent a negative number using symbols. Remember that number used to be -1. What does that even look like? And fundamentally, the problem here is that transducers have this monotonicity property. If I add more symbols to the input tape, the output tape can only add more symbols. So I sort of need to be able to add symbols to create negative numbers. That seems a little bit hard. And so fundamentally, I can't do subtraction, which is what I needed to do to represent this kind of negative skew. So how do we fix it? How do we make transducers, which are the way that we're going to be, and these automata, which are the way we're representing recursive iteration spaces, handle subtraction? So to do that, we're going to take a detour to thousands of years ago. So how did Brahmagupta handle negative numbers? So Brahmagupta handled negative numbers by representing negative numbers as a pair. In fact, all numbers as pairs, not single numbers. You call them fortunes and debts. Okay? And the way that you represent a number is you just represent a debt and a fortune, and the value of the number is the fortune minus the debt. Okay, so you get equivalent classes of pairs that represent each number. This number represents one more fortune than debt. This number represents 1, this number represents 1, a bunch of different ways of representing it. But the nice thing when I'm using fortunes and debts is that I can also represent negative numbers. This is how we represent negative numbers. If I have more debts than fortunes, I'm in debt. What's a negative number? And now I can do subtraction using just addition, effectively. If I want to do 1 minus -1, I just swap the debts and fortunes of -1 and add them to 1. And so I get a new number here that represents 2, which is exactly what I should be getting. Right? This is how I can do subtraction using just addition. And that actually maps to the way we handle control words. So existing control words, the way that polyrec handles this is you can think of them as basically only ever accounting for fortunes. Adding more symbols makes your number bigger. So if I want to add a symbol here, I go from 1, 0 to 1. What if I also add negative symbols? What if I allow myself to add negative symbols that work like debts? So now I have this number here that represents 1, 1. Don't worry exactly about those T1 and S1, but underlying numbers represent negative numbers here, negative symbols. Now if I add a new negative symbol, it's like adding a debt, and I'm able to decrement the value out of that. And so I can extend this to my iteration space automata, and I can extend this to my transducers. So in the existing automata, my tape is basically positive. I'm only ever adding symbols and adding to where my control word is. If I add a symbol, the control word moves forward in time or later in the schedule. But if I add a negative tape, so now every tape gets another matched negative tape that basically acts as negative symbols. Adding symbols is going to move the control word backward in time. This is the way that all the ordering works out. Don't worry about the details. Fundamentally, though, if I take this purple iteration and I add a negative R2 symbol to it, it basically has the effect of giving you the control word for the pink iteration and moved backwards in time, even though I added a symbol. And now I can subtract with transducers. I basically just subtract by adding symbols to the opposite polarity tape. I can represent this kind of negation using this kind of rewrite. Don't worry so much about staring at this and figuring out what it means, but basically what I'm doing is I'm just adding to the opposite tape. I'm taking the positive symbol and adding to the negative tape. I'm taking the negative symbol and adding to the positive tape. It lets me do subtraction in my transducer. So now I can represent arbitrary linear transforms. In fact, the paper shows a procedure for taking any arbitrary linear unimodular matrix, in fact, any arbitrary linear transformation matrix, and constructing a transducer that captures it. So now I can handle any of these unimodular transformations in this framework. They still compose, they still have the same effects. But it doesn't actually work. Seems like it works. It looks really cool. We're able to handle subtraction, but it doesn't quite work. So here's the problem. If you remember back to when we talked about what makes something a good iteration space representation, we had two criteria. One was that each dynamic instance of a statement needs a unique name. We need to name each dynamic instance uniquely, but of course the entire point of these Brahmagupta style numbers is that we don't have uniqueness anymore. We're representing numbers using equivalence classes, and there's multiple control words that actually sort of correspond to the same number that we want to talk about. Right? There's multiple, in fact, there's an infinite number of ways to represent one. I also need to make sure that my dynamic instances are totally ordered into some schedule. They actually have to give me an execution order. But this doesn't work anymore either. Because now that I have two different ways of naming this 1-1, if I take this iteration for 1-2, which should come after 1-1, comes later lexicographically, it's actually before one of those versions of 1-1 and after the other one. Right? So I've broken ordering. Depending on which version of 1-1 I'm looking at, I no longer have the correct ordering of control words. So I've been able to handle subtraction, I've been able to handle these transformations, but it actually doesn't work as an iteration space representation anymore. It's failing both of those problems. It's failing both of those criteria. So here's how we fix it. What we do is we define a representative of each one of those equivalence classes that we call the canonical control word. The way to think about a canonical control word is it's basically just a control, like a version of the control word that either only has negative symbols or only has positive symbols in each dimension. It doesn't have both. Right? So I just cancel out fortunes and debts. And once I think of canonical control words, those guys are actually properly ordered. There's one word, there's a unique name for each instance, and they are correctly ordered. Great. How do I do that? How does that help me? How does having canonical control words help me? Well, it turns out I can build a transducer that does canonicalization. I can build a canonicalization transducer that takes arbitrary control words and cancels out matching symbols so that I get canonical control words out the back. Okay? And because it's a transducer, I can compose it with everything else. So I can build my giant composed transformation doing arbitrary linear transformations, and then stick this beast on the back. And this, don't worry about the details, it's in the paper. I can stick this beast on the back, and what I get on the other end is a bunch of canonical control words that are correctly ordered. And so now I'm back to having a working iteration space, but one that can handle negative numbers. There's a lot of other details in the paper, including some restrictions that we have on what kind of transformations we're allowed to do. We still handle all of unimodular. And in particular, how we deal with dependencies. So if there are dependencies in the program, not all transformations are safe. You need to be able to figure this out. PolyRec spent a lot of time coming up with a decidable dependence test for this. There's not a lot of things that are decidable about multitape automata. This is one of them. And we showed that we can still do it in this world of sort of doubled up multitape automata. And so really quickly, what this buys us, we evaluate it on a bunch of different programs, including things like this that look like trees of arrays that are being manipulated in crazy ways. The dependent structures in these programs mean that you cannot parallelize these codes unless you do something like skewing to run them in a tilted way. And we show that we can represent the transformation, we can reason about the transformation, show that it's safe, and unsurprisingly, when you parallelize these, you get better performance. So that's UniRec. It's a general framework for handling loops and recursions. In order to do that, we came up with a new representation for iteration spaces. In particular, one that lets us handle arbitrary linear transformations, so we can cover all of the unimodular transformations, including skewing, and a dependence test that kind of lets you, at the end, make sure that all your transformations are accurate. And so, fundamentally, UniRec generalizes and unifies the reasoning that people do for perfectly nested loops in the unimodular framework, and the reasoning that we do for nested recursion in polyrec, and so now we have a fully general system. And with that, I'll take questions.
So this might just be the example you showed, but I'm going to ask to make sure. So in your example, you showed this like square iteration space. You're taking I goes from 0 to n, j goes from 0 to n. Are you able to do anything like triangular iteration spaces, like I goes 0 to n, j goes 0 to I?
So this is a great question. And in fact, the I goes from 0 to n and j goes from 0 to I, those are exactly the kinds of loop bounds that you wind up with when you do certain kinds of skewing and certain kinds of unimodular transformations. You get these dependent loop bounds. In the loop world, we do. One of the dirty secrets about UniRec is that we don't have like a great story for code generation right now. We know how to do code generation to generate those kinds of things. There's examples in the paper. The framework itself is mostly reasoning about whether the transformation is sound. The way the code generation works is you then go in and the compiler will have to just sort of individually apply these kinds of things. But you absolutely can handle it. UniRec and polyrec more generally is more focused on the way that we're transforming these orders, and the loop bounds, which is mostly about code generation, is handled by an automated process.
Okay, now, for doing loop reversal in polyrec, will be negative numbers?
Okay, so this is a great question, and the answer is no, because we cheated in polyrec. So the way that we do loop reversal in polyrec is by doing this pre-order to post-order transformation, which is what that transformation actually does is just change what counts as alphabetical order in our symbols. It's not actually a negation. It turns out that is equivalent to moving all of the positive symbols to the negative key in terms of what effect it has. So UniRec handles reversal in the kind of more classic actually reverse things way. Polyrec does it in this kind of cheating way of going from pre-order to post-order.
So it seems like the major effect is to change the access pattern of objects in memory.
That's right.
So there's two parts, right? There's construction of the data structure and then the traversal of the data structure. Have you thought about like connecting analysis of one part of it to the other part?
That's a really good question. So we haven't, and this is one step in a pretty long process of like trying to recreate a lot of what people have done for basically for matrices in the world of recursive stuff. We have a completely separate project that's not actually unified with this at all. It's about doing good data layouts for things like trees and lists based on looking at the traversal orders and stuff like that. I haven't even begun to think about how to try to unify those two ideas, but it's a good point. Polyrec and UniRec are really focused on traversal after the data structure exists.
So I'm not an expert in this case, but I'm kind of curious.
Yeah.
So you presented skew as an important for parallelism, but it was unclear to me that negative skew was actually necessary for parallelism. So do you need negative skew? And what does it look like when you actually do implement that negative skew? Is that a desirable thing?
Right. so this is a good question. So in general, the thing that I basically didn't talk about at all in this presentation is dependencies. Right, dependencies between iterations, because I might be like one guy might be reading from an array that another guy is going to write to. And unsurprisingly, when you reschedule a computation or parallelize a computation, you have to make sure the dependencies are respected. For example, if you do something like Gauss-Seidel iteration for a stencil code, you wind up with this kind of wavefront style computation where there's sort of a wave of anti-diagonals that you have to execute one after another. And so in order to do that in parallel, what you need to do is essentially tilt the iteration space so that the anti-diagonals now look up and down. Now, negative skew, the thing that's a little bit confusing here, and this actually tripped me up the very first time I taught this material. Even though there's a very close correspondence between the way those iteration spaces look and what the actual matrices look like, the data is not actually changing. The matrices are staying exactly the way they are. What's changing is the index expressions into those matrices. So it's okay if I and j wind up as negative numbers. You update the index expressions to do the correct computation so that you actually wind up accessing the right parts of the array. So it's just, if your dependencies happen to be tilting this way instead of tilting this way, then you need to do a negative skew instead of a positive skew. So yeah, it's a really subtle thing to think about. Like I said, I got it wrong. I tried to teach it the first time.
Do we have the last question? All right, then let's thank our speaker.